started recording already. I want to say something not very appropriate. Right. So over we just look at the equivalent load. Okay. So the equivalent load is half times 6 times 10 to the power 3. And then the distance from here to here is going to be 2/3 multiplied by a distance of 6. Okay, so that's the distance. So this is equal to 4 meters. Now you'll be wondering, hey, what is going on, man? What is going on, man? Okay, I'm going to explain to you what's going on. Okay, so this is probably, some of you will remember, if you will do this in colleges, probably have seen this before. Those of you that have not, don't worry about it. Okay, so I'm going to, right. So there are two types of distributed load. Okay, so there's one type known as evenly distributed load. Okay, so this is one type of distribution. Okay, so there's one known as evenly distributed load. So on evenly distributed load, so if we have a beam, okay, we have a beam. This is our evenly distributed load, and then one end is on a pin. The other end is on a roller, and then this is our evenly distributed load. Okay, so this is our load. And then they will quote that this is omega, which is Newton per meter. So what does this actually means? Okay, so mathematically, so if now I'm going to draw different axes now. Okay, so one axis is x. Okay, so this is x, and the other axis will be omega. Right, will be omega. So we will have a distance from here to here is L. So this up to here is L, and then we have our omega. Okay, so this is the area. Okay, so this is our graph, right, of our distributed load. So the equivalent load will be equal to omega times L. Okay, so if you look at that graph, omega times L is the area under the line. Okay, so the area is known as the equivalent load. Okay, so if we were to draw our free body diagram, right? So if we were to construct our free body diagram, right? So this is our free body diagram. So we know that we have a reaction at this, we have a reaction over here. Okay. Now I do apologize. So let me call this point A, and let me call this point B. So you'll see that over here, you have a AY by following the same transformation that we have. This is BY. And over here, which is your equivalent load, which is omega L. Because it's equivalent load, the centroid is exactly L over 2 of the equivalent load that's acting on. Okay, it's L over 2. So now this is for evenly distributed load. Okay, this is evenly distributed load. Now let's look at a gradient. So what we have is not evenly distributed. What we have is a gradient distributed load. So we are going to draw, next thing, we're going to draw a gradient distributed load. Okay. So likewise, we have our member AB. So now the load, okay, so again, we have one point that's pin, the other point is on a roller, point A and point B. So now this is different now. Okay, so we have a gradient now. Okay, we have a stupid thing. I'm so pissed off with Microsoft now. You guys just don't know. Okay, but anyway, so this is our gradient distributed. You piece of crap. Okay, sorry. So this is our gradient distributed load. So what is quoted when the magnitude is given is this magnitude over here, which is omega. Okay, again, they quote it as Newton per meter. So mathematically, okay, we again have our axis. Okay, so this is our axis. So this will be our x. Okay, and same thing, we also have our length from here to here. This is L. So this over here is L. And then we have our omega over here. So we have a gradient. I wonder why it only allowed me to draw until there. So this is our gradient, straight line. Okay. And then stops down here. Now, so this is how the distributed load look like. Okay. So the equivalent load, the area will be the what? Equivalent load, right? That is why the equivalent load that we have calculate earlier, what did we say the equivalent load is? If you calculate over here, it's what? Half base times what? Height. But I'll go further to explain why is that. So why is it half base times height? Okay, so the equivalent load we know over here is equal to what? Is equal to half times omega L. Okay, half times omega L. So mathematically, the function, right? The function of the distributed load of the gradient distributed load is equal to omega as a function of x, and the gradient is equal to the change in y over the change in x multiplied by x plus by 0, y 0, because the y-intercept is what? For this case is equal to what? 0. Okay, so the function happens to be omega x is equal to omega over Lx. Okay, why is that? Because the slope over here, the gradient over here, is a change in omega. Over here is a change in what? Length, or the change in x. Okay, the change in x. So to find, the area, the equivalent load, to find the equivalent load, which is the length under the straight line, or the area under the straight line, you integrate from the limits of 0 to L, okay, omega as a function of x dx. Okay, now does this look familiar now? It bloody does. It's from your math, yes or no? Right? Yes. So you have been learning a lot of math. Now we are applying the math now, okay? So we know that we are going to integrate, right? Now my integration are Mickey Mouse stuff. What you learn in the math is advanced integration, okay? But you it's more of interpretation, how you interpret your results, okay? More important. So this is omega over Lx dx, okay? So this will be equal to omega x squared divided by 2L, and then we integrate between 0 to L. So this will be equal to omega L squared divided by 2L. So you cancel. So this is equal to omega L over 2. So I'd like to draw your attention. This is exactly the same as this. Okay. So now the next thing is the distance, right? So this distance is pretty straightforward. For the evenly distributed load, the distance is very straightforward, right? You see that's the distance, good. Whereas for a gradient distributed load, okay, the gradient distributed load, right? So the gradient distributed load okay, and again, I don't want you all to memorize this. So as usual, we construct our free body diagram. So this is your AY. This is your BY. Over here is your equivalent load, omega L, okay, omega L over 2. And the distance from here to here is 2 over 3L. And the distance from here to here is L over 3. Okay, let me, and that distance over there is L over 3. Okay, again, I don't want you to memorize this. Okay, I want you to, why is it 2L over 3? Why is it L over 3? Okay, so I'm going to, it's very simple to do this, okay, if the computer cooperate. So I'm going to draw a right angle triangle now. Okay, so this right angle triangle that I'm going to draw will have 9, bloody hell,